Just wait one second, Pritam. So I just sit. Okay, so welcome back to lecture 11 on Riemannian symmetric space. Okay, so in the last lecture we have seen that SPN is really connected. And we have also seen that we have defined something like GLNH. GLNH is really, this was T belongs to GL to NC, so that Tj is equal to J bar T. And similarly, I have also seen that SLNH really T belongs to SL to NC, so that Tj is equal to J bar T. This condition actually really says that T respects the scalar multiplication by J. Multiplication by J. So we have also seen that this SLNH is nothing but GLNH intersection SL to NC. This much we have seen. Okay. Now SLNH actually you can write that like this is SLNH. You can also write like this AB minus B bar A bar, so that determinant of AB minus B bar A bar, this is equal to 1, and A comma B belongs to NC. Okay, now this gives an embedding of SLNR inside SLNH, and this is, so you take A and you simply map to A 0, so A belongs to SLNR. So easy to say that. So thus what we get this SLNR. This is subset of SLNH, and this is subset of GLNH. Okay, so now this SLNR is really unbounded. This implies SLNH and GLNH are non-compact. Now we want to really recall for any for any subgroup of GLNH, we have two pictures. One is in the quaternion picture itself, and we have an embedding inside GL2NC. Okay. So and we will go to move towards the connect to showing that GLNH and SLNH are connected. We will show that GLNH and SLNH are connected, and for that we will use that polar decomposition lemma. So for that we will use this embedding inside GL2NC. Okay, and for that reason that we have to show that this really GLNH is closed under conjugate transpose. Okay, so okay, one thing I have also mentioned this last time clearly. This GLNH and SLNH are pseudo-algebraic. Okay. So ideally, I should really, so this, if you recall this polar decomposition lemma, that is This is for over the field complex number. Okay, so ideally I should show that this set right hand side t belongs to GTL to NC, so that Tj is equal to J bar T, that is actually closed under conjugate transpose. But since we have a relation like this thing, Z of we have this relation Z of A star is equal to Z A star. Okay, or A belongs to MNH. So this is equivalent to saying that you can show, uh, you can use this fact that uh, in any picture, like in quaternion picture or complex picture, if you can show that in any of the picture that that group is closed under conjugate transpose, then you are done because of this relation Z A star is equal to Z A star. So what I am saying that, see, the thing is to show that to apply that polar decomposition lemma, we need that condition that the group should be closed under conjugate transpose. So you can do that for any picture, quaternion picture or complex picture. Okay, so that is what I am saying. So, but in this case, I will use this complex picture, so there is no problem at all. So claim if A belongs to this GL. This implies A star belongs to GL. To show that, so A belongs to GL, what does that mean? This means A belongs to GL2 and C, and AJ is equal to J bar A, J A bar. Okay. Now, so if A belongs to GL2 and C, this clearly implies that A star belongs to GL2 and C. Sorry, I should. Okay. Since A belongs, okay. Now we have this thing AJ is equal to J A bar. I will take the transpose in the both sides. So I will get the J transpose, A transpose. So A bar transpose and J transpose. Now J is your matrix 0, I minus I0. So J transpose is equal to what? 0, I minus I0. And you can see that this is really nothing but minus of 0, I minus I0. So J transpose is equal to minus of J. So I will use that fact here. So J transpose I will replace minus J. A transpose is nothing but A star bar, and A bar transpose is equal to A star, and this is minus C. So this is minus of, okay, so this implies J star bar is equal to A star J. Okay, so A star belongs to GL2 and C, and J star bar is equal to A star J. This implies A star belongs to GL and C. Okay. Now since determinant of A star is equal to determinant of A bar, it is also clear that SLNH is closed under conjugate transpose. Okay, so now the thing is, I want to, okay, so what is my SP? So SPN is nothing but this is A belongs to set up all A, so that A belongs to GLNH and A star A is equal to identity. Okay. So I like this, then I will get Z of SPN. This is equal to ZA, so that A belongs to GLNH, and this condition, so A star A is equal to identity, so this will imply that Z of A star A is equal to Z of identity, and I apply the properties of this map Z, so I will get ZA star ZA is equal to identity. So I write that here, so this is equal to ZA star ZA is equal to identity. So look at this right hand side very carefully. So right hand side is what? This, if you look at, this is nothing but Z of GLNS intersection U to N. Okay, so I am getting that Z of SPN is equal to Z of GLNH intersection U to N, and I can same thing write that same thing as in the complex picture. T Z, if I will replace Z by T, so that T belongs to GL to NC. Okay, so T star T is equal to identity, and there will be another condition, Tj is equal to Jt bar. Okay, so this is my thing. Now, as I said that I do not really want to write Z everywhere, so I will remove that. So SPN, I will get that, so GLNH intersection U to N. Okay, now this SPN is connected. So by that polar decomposition thing, because we have shown that GLNH is pseudo-algebraic, so by polar decomposition, we get that GLNH is connected, and I1 of GLNH is SPN, I1 of SPN. So this is clear. Now I write, let us go to the, now SPN is really what T belongs to GL to NC, so that Tj is equal to Jt bar and T star T is equal to identity, and this is the realization of SPN inside the complex group GL2NC. Now, okay, so what will be Lie algebra of SPN? This will be X belongs to GL2NC. Okay, so if I will use this thing, so that will give you, this is Xj is equal to Jx bar, and similarly this condition will give you this X star plus X is equal to 0. And if you want to really write in the bottom, yes sir.
Why should X be inverted?
Yes sir.
Why X is in GL2NC?
Oh, M2NC sir. Yeah, thank you sir. Actually, I really did it. Thank you sir. Thank you sir. X belongs to M2NC. X belongs to M and X, so that X plus X star is equal to 0 in the quaternion method. Okay. Now there is a one other thing that you know this on Rn. So take the standard inner product, you get O to N, and in the Cn you take the inner product and you get, sorry, you On. You get On, and in that case you get un. Okay, now in the case of hn, you get this spn, right? Now if you add this condition that determinant of a is equal to 1, then in case of rn you get this son. Okay, and in case of un you get this sun. And question is whether you get something in this case spn case. Okay, and you will see that you will not get anything because determinant will be always 1. Okay, now let us write this. So spn, let us write once more this definition of spn, so that this t belongs to gl2 and c, so that tj is equal to jt bar and t star t is equal to identity. Okay, now the thing is so tj is equal to t, so let tj is equal to jt bar. Okay, so and t belongs to gl2 and c, so this condition will give you. Okay, now okay, so you know that j square is equal to minus identity, so that will give you minus j square is equal to identity, so that means minus j into j is equal to identity, so that gives you j inverse is equal to minus c. Okay, will you use this fact? So you multiply a j inverse in both sides. Okay, minus j in both sides, minus j tj is equal to minus j square and t bar, and minus j is your j inverse, this is t and j, minus j square is equal to identity, so this is equal to t bar. Now you take determinant in both sides, so determinant is a conjugation invariant, so you will get determinant of t is equal to determinant of t bar, and this determinant of t bar is nothing but determinant of t bar, so that means determinant of t is a real number, this belongs to R. Okay, so tj is equal to jt bar, this means determinant of t is below to R, this is 1. Okay, so tj is equal to jt bar is giving me that determinant belongs to R, and we will use this also later. So now second thing is there is something. So okay, so let t star t is equal to identity. So if you put this determinant in both sides, determinant of t star t is equal to 1, and so determinant of t star into determinant of t is 1, and this, okay, so determinant t star is determinant of t bar, so this is mod of determinant of t square is equal to 1. Okay, so this is true, say. So now if if t belongs to Spn, then it will satisfy both these conditions, and determinant of t is real and determinant of t square mod t square is equal to 1. So that means if t belongs to Spn from 1 and 2, we get determinant of t square is 1, and determinant of t is plus minus 1, plus 1 or minus 1. Okay, now you know that Spn is connected, so determinant from Spn to plus minus 1, plus 1 and minus 1 is continuous, and as Spn is connected, this implies determinant of Spn is constant. Now since identity belongs to Spn, this, so determinant of Spn is equal to 1. Okay. So what I am getting, thus we get SPN is contained inside SL2NC. Yeah. So this is clear. Now, so we have already, we know that SPN is equal to GLNH intersection what U to N, and you get that SPN is contained inside SL2NC. So you can get that this is same thing as GLNH intersection SU to N. Now since SPN is contained inside SL2NC. Okay. So now you compare this thing compare with the relation which you have get this UN is equal to GLNC intersection O to N and GLNC intersection SO to N. You really compare with this relation. Okay, so now another thing, SPN is contained inside SL2NC. Okay, so this implies SL2NC intersection SPN is your SPN. Is clear? Now I will use this relation. SPN is equal to this G. SPN is equal to GLNH intersection U to N. Okay, L in the left hand side. So I will get SL2NC intersection in place of SPN. I am just writing this GLNH intersection U to N is equal to SPN. Okay. So this is the thing. Now GLNH intersection U to N is nothing but what? SPN. So now I also know that these first two things is okay. So let us write another line then. This will be SL2NC intersection GLNH intersection U to N is equal to SPN, and SL2NC intersection GLNH is your SLNH. So SLNH intersection U to N is equal to SPN. Now SPN is connected and SLNH is pseudo-algebraic and closed under conjugate transform. This implies SLNH is connected and pi1 of SLNH is equal to your pi1 of SPN. So Pendu, is this clear?
Yes, Mara.
Okay, so we have seen that SLNH is connected and this thing. Now we move towards something called as PP, Q. Did I leave something? Yeah. So this is okay. So now this thing actually, since this SPN inside SL2NC, you can get actually various relations. For instance, you can see the thing is sorry. So I am not writing these relations because there is no. So SLNH intersection U to N. Same thing you can write. This is SLNH intersection SU to N. You can write various relations, but these are not important that much. So we'll move to start something called as PP, Q. This is pseudo symplectic group of signature P country. Okay, so let U comma V belongs to H E plus Q. I define this Hermitian form H U V. So this is really M is equal to 1 to P U M bar P M minus N is equal to P plus 1 to P plus Q, this Q M bar V M. And this H is a really, this is a non-degenerate H Hermitian form. Okay, so this is one thing. So, and associated matrix analogous to the complex and the real case, will be get associated matrix will be this IEP comma Q. So this SP P comma Q, I am just writing this matrix thing. A belongs to M P plus Q H. So this will be A star IEP comma Q A is equal to IP comma Q. Okay. Now this I want to really go back to the complex picture, and so this will be T belongs to, and this is uh, the dimension of this is dimension of the matrix is P plus Q in the Hermitian thing, and in the complex it will double the dimension. So this will be M 2P 2Q C, and first condition will be something like JT is equal to TJ bar, and let us see what this condition is really. Okay, that so this is A star I P comma Q A is equal to IP comma Q. So if you put Z in the both side, so you will get this Z A star Z of IP comma Q into ZA is equal to ZIP comma Q. Okay. Now this will be ZA star ZP comma Q. I am calling KP comma Q, and this Z is equal to KP comma Q, where this KP comma Q is equal to Z of IP comma Q, and this will be something like IP comma Q, okay, IP comma Q, and this will be 0 0. Okay, diagonals IP comma Q 0 0, because that is, you know, that Z of AB is equal to A B minus B bar A bar, so that will be. So I write that ZA is equal to T, I replace that, so I will get this T star KP comma Q T is equal to KP comma Q. So I should, okay, let us write this KP comma Q is IP comma Q 0 0. Okay, so now let us go to the next page. So I will get what this SP P comma Q. I am getting the T GL to P plus 2 QC, so that TJ is equal to JT bar, and T star KP comma Q T is equal to KP comma Q. So this is clear that clearly SPP comma Q is pseudo algebraic. There is so now SP P0 and SP0 P0 Q. These are really compact symplectic groups. So we will assume this P greater than equal to 1 and Q greater than equal to 1 onwards. So now look at this definition, this first definition, A belongs to MP plus QA, so that A star IP comma QA is equal to IP comma Q. So this will say that OP comma Q is and UP comma Q both are contained inside SPP comma Q. So from definition of SPP, so OP comma Q is constant inside UP comma Q, and this is SPP comma Q. Here actually I am using this quaternionic picture. Okay, so this is unbounded, so this implies SPPA is non-compact. So you have to really show that claim. Okay, before that, so let us use to be something like that. So let A belongs to MNS, B belongs to MNS. Suppose AB is equal to identity. AB is equal to identity. Can I say that AB is equal to BA is equal to identity? So in finite dimensional case, this is clear. But the thing is, you know that in infinite dimensional case, this result is not true. So you should not rush into the conclusion that BA should be identity. It is true that BA is identity, but you have to really be very careful, because it is not a vector space over a field. It is a vector space over C field. And whenever there is ambiguity, you always really use that embedding map Z. Okay, this is clear, because proof is very simple. As I said that you always AB is equal to identity. This implies Z of AB is equal to identity, Z of identity. So this implies ZA, ZB is equal to identity. Now ZA and ZB are complex matrices. So therefore you can write that ZB ZA is equal to identity. And this is Z of BA is equal to identity. So that will imply that so this implies BA is equal to identity. So this is clear. Okay. So claim A belongs to SPP comma Q. This is A star belongs to SPP comma Q. You can really use the complex picture and prove that if A belongs to SPP comma Q, this implies A star belongs to SPP comma Q. But I will use that quaternion picture to just to show that there is no difference at all. So okay, since ZA star is equal to ZA star, it is sufficient to show transpose in the quaternion picture. Okay, I am just writing this because this is thing. So A belongs to SPP comma Q. This implies this is A star IP comma Q. A is equal to IP comma Q. Now you apply that exactly same kind of argument which I have given you. So IP comma A star IP comma Q A is equal to IP comma Q square is equal to identity. Now this is my A and B in the previous and we are in the quaternion setup. So that will give you IP comma QA, IP comma Q A star is equal to identity, and if you multiply IP comma Q in the left, you will get A IP comma Q A star is equal to IP comma Q, and this is A star star is equal to. So this implies A star belongs to where SPP plus Q. So you can you can take it in exercise that you show this thing in the complex picture. Okay? So this is the thing. Now I want to really find what is this thing. Okay. So what is this SP? Okay, I want to really find this SPP comma Q intersection U2P plus 2Q. Okay. So this is same thing as okay. So this is actually subset of GL P plus QH intersection U2P plus 2Q. Okay. Now what is GLP plus QH U2P plus 2Q? This is nothing but right hand side. This is nothing but SP P plus Q. We have shown that since we have seen the since SPN is equal to GLNH intersection U2N. We have put that, so SPPQ. Now, okay. So SPP comma Q, okay, intersection U2P plus 2Q. Since this is contained inside SP P plus Q, so I can take intersection in one side. So this is the thing. The SPP comma Q intersection U2P plus 2Q is equal to SPP comma Q intersection U2P plus 2Q intersection SPP plus Q. Now from this relation that SPN is equal to GLNH intersection U2N, that SPN is a subset of U2N. So this U2P plus 2Q intersection SPP plus Q. So this will be really SPP comma Q, and that will be really SPP plus Q. Riju, it is clear?
Yes, Kumar.
Okay, so this is the thing. So position. So this is SPP comma Q intersection SPP plus Q. So this will be something. Okay. So Pritham, can you make a guess of this thing? Yes, what will be SPP comma Q intersection SPP plus Q? Pritham, are you there or?
Yeah.
Can you make a guess? Okay, this is the same thing with O, P, Q, comma K case and U. So this will be A00B, so that A belongs to SPP, B belongs to SPQ. Okay. So this is actually proof. So proof argument is exactly similar. Similar argument as in the case of OP comma Q or U comma P. You can do this thing. I will not do this thing because it is more or less exactly the same argument. Only Euclidean inner product you have to replace by this so-called quaternion inner product, and some minor change of symbols are there. So what I am getting? So I am getting this is hence we get this SP P comma Q intersection U 2P plus 2Q. This is same thing as SP P comma Q intersection SP P plus Q, and this is SPP cross SPQ, and this is SPP is connected. So and this is connected, therefore product is connected. So this implies SP P comma Q is connected by polar decomposition theorem, and pi 1 of SP P comma Q by pi 1 of SPP. So this SPP comma Q is a non-compact group and it is connected, and we have also information about polar decomposition theorem. Now we will move towards SP2NR. This is a I have told you that let U P Q prime B prime, this belongs to Rn, and here is the simplex Fibonacci W of UB U prime B prime the U dot P prime minus B dot U prime. So associated matrix you can is J1, and okay, so associated matrix with respect to standard basis. So whenever I am not mentioning the basis, that means I am taking the standard is your J1, and this J1 is nothing but 0 I minus I0, and this is nothing but minus of 0 I minus I0, and this is really the standard complex structure J. So this is equal to minus of J. This, so remember that thing. So what I will get? This SP2NR is really A belongs to M2NR, so that A transpose J1 A is equal to J1. So this is really, you can, since J1 is equal to minus J, this is same thing as A belongs to M2NR, so that A transpose JA is equal to J. So this is the same thing. And one thing actually which I should have told you in the beginning, if you look at the books, everywhere books write this A belongs to GL2NR. They do not write that A belongs to M2NR. Okay, they simply write A belongs to GL2NR. Okay, and I told you that these two things are equivalent. Suppose you really write this A belongs to GL2NR everywhere and you do not know the connection, then what you will do was to show a matrix A belongs to SP2NR, you will check this condition A transpose J is equal to J. Then one more condition you have to check, A belongs to GL2NR, A is invertible. That is extra work. For that reason, actually, I am not really putting M2NR, GL2NR, depending upon my convenience. For instance, if you to show a matrix is an orthogonal matrix, you first show that if you stick to this type of definition, you first show that columns of A forms an orthogonal basis. Then after that, you show that A is invertible. And this is not a very this is a you are doing some extra work. For that reason, I am really writing A belongs to M2NR. Okay, so this is same thing as A belongs to GL2NR, so that A transpose J is equal to J. So clear that okay, so clearly this SP2NR is pseudo-algebraic, and there is one more important thing, that this is actually a anti-symmetric bilinear form. This is a anti-symmetric non-degenerate bilinear form. Okay. So this is really the thing. Clearly, SP2NR is pseudo-algebraic. Now, my claim. So okay. So this GLNR sits inside SP2NR. GLNR, there is an embedding of GLNR inside SP2NR. And what is the map? This is A going to this A0, 0 A transpose inverse. Okay. Let us check that. So A belongs to GLNR. So let us check that. Let T is equal to A0, 0 A transpose inverse. So what I have to check, this T transpose JT. So this is really A0, 0 A transpose inverse, and J is your 0I minus I0, A0, 0 A transpose inverse. Okay. So if I multiply that, so first will be 0, 0 minus A, and so I am multiplying the left things. So the 0 A transpose inverse, and this is 0. So A 0 A transpose. Okay. So now if you multiply this thing, 0, first thing will be 0 and 0. Did I do it something somewhere wrong? Yeah, I did a wrong thing. Okay. Okay. So T transpose. Okay. T transpose. Actually, I have put wrong. Look at this thing. I have to write that T transpose. So this will be A transpose. And when we will take transpose, so this will be A inverse. Sorry. So the first thing will be, I have to calculate first thing. So first thing is A transpose. So this is 0. This is minus of A transpose. So this is will be A inverse. So this will be 0. So 0, 0. So this will be minus of identity, and I 0. This will be okay. So this will be J. So this implies T belongs to sp to nr. So we have an embedding of GLNR inside sp2nr. So that means sp2nr is non-compact. So since GLNR inside sits inside sp2nr, and this is really unbounded, this implies this sp2nr is non-compact. So pseudo algebraicness is I have shown that claim actually. So let A belongs to the sp2nr, and since here I am really it is a real matrix, so I have to show that A transpose belongs to sp2nr, and this is very clear proof. It is so let A belongs to sp2nr, so this implies A transpose J is equal to J. Here I will multiply this minus J. So this will be minus of J square, and this is equal to identity. So I again use the same kind of argument. So this will be J into minus of J transpose is equal to identity. Now you multiply minus J again, J again both sides, so J square A minus J transpose, this will be J, and J square is equal to minus 1, you use that, so AJ transpose is equal to J, so you will get A transpose J transpose is equal to J. So this implies A transpose belongs to sp2nr. So this implies sp2nr is actually closed under conjugate transpose. So I have to use the utilize that polar decomposition lemma. So for that I need to really calculate this sp2nr intersection of u2n. What is this? It's coming. Now this is really since sp2nr is a real matrix, this is same thing as sp2nr intersection O to n, because these are real matrices. Okay, so now I want to prove a proposition. Okay, so what I did, sp2nr intersection O to n and is equal to un. I have told you that this doesn't have any meaning, because left hand side is a 2n cross 2n matrix and right hand side is n cross n matrix, but we can give a meaning to it. So we call this A. The meaning of A is nothing but this thing, sp2nr intersection O to n is equal to z of un. We'll prove this A prime. So this, so proof I will prove of A prime. So let U belongs to say MNC. Okay. So you have shown that U of x plus IY is U of x prime plus II prime, this inner part on Cn, where x, y, x, I, x belongs to Rn. This is same thing as ZU applied on xy and ZU applied on x prime, y prime, and this is norm on R2n minus IW, this is ZU xy and ZU x prime So this is the thing we have shown in some previous lecture. Let me show that. So in okay, so this look at this relation. This one relation u of x plus iy u of x prime plus iy prime is equal to z u x y inner product of z u x prime y prime, and this inner product is in R2n. Sorry, this is on R2n, and we have seen this in some previous lecture. And let me code it. It is page 127.1. So this is really call this as one. Okay. So C 1 of it. I am writing C 1 of page 127. Okay. We have proved that. So that means suppose U belongs to unitary matrix. So that means it will preserves the inner product of Cn. So this will be observation. We have this observation from 1. This is the thing that U belongs to Un if and only if this implies. Okay. So let us write this if and only if ZU belongs to where? O2N intersection SP2NR. So from this equation, you just take it some time to think. Okay, so U belongs to UN if and only if ZU belongs to O2N. So this thing, actually this observation, it is clear from this from the above observation. It is clear that Z of UN is really contained inside O2N intersection SP2NR. Bootstrap, it is clear.
Yes.
So Z of UN is intersection O2N intersection SP2NR. Now I want to prove the converse. So let us T. Let T belongs to O2N intersection SP2NR. So since T belongs to O2N, I will get A transpose A is equal to identity. This is same thing as A transpose is equal to identity. Okay. Now as T belongs to SP2NR, so this will imply that what? Oh, actually I should write here A. Sorry, I missed. Okay, as A belongs to SP2NR, so this is A transpose ZA is equal to Z. Okay. Now I use this fact that A transpose is equal to identity. So I multiply that A in the, so A transpose JA is equal to AJ. A transpose is equal to identity, I use that. So this will gives me JA is equal to AJ. So this condition, this, and where is A? A is belongs to some matrix in GL2NR. Okay. So this condition, it says that A is equal to ZU or some U belongs to MNC, because this is really now. So now ZU is equal to A, we have taken that this belongs to O to N intersection SP to NR. So by the observation from previous page, we see that U belongs to UN. So U belongs to UN. We are getting now A is equal to, this implies A is equal to ZU belongs to A is equal to ZU. This belongs to Z of UN. So I have started an element from O to N intersection SP to NR, and I am getting that in ZUN. So this implies what I am getting O to N and intersection SP to NR. I am getting this is really inside Z of UN. So hence hence the proposition, hence the proof of a prime. Okay, so hence we get this. Let us write that Z of UN is equal to O to N and intersection SP to N. Okay. So as I told you that okay, so what I am getting, this SP to NR intersection U to N, actually SP to NR intersection O to N, and this is I am getting what, UN. This UN is connected, so this is connected. This implies SP to NR is connected, and pi 1 of SP to NR is equal to pi 1 of UN. This is about SP to NR. We will move towards SP to NC. So this is really the same thing. Actually, I will leave some details that U prime instead of Rn, I to towards I take Cn. So W UV U prime V prime. So this is equal to U dot V prime minus V dot U prime, and this is a same thing as non-degenerate. Oh, I sorry. Okay, I left a small detail thing actually. So I will come back to it. So just 1 second. Okay, so just a small thing that in case of bilinear form, suppose you get this thing. Suppose O P comma Q. Actually, I have left two details in this. Okay, sorry. Okay, so let me actually first this thing. This SP to NR. The question is, if you take this determinant of A is equal to 1, do I get any extra group of not? Okay, so that is you can do it because by the same argument. And so for the completeness, let us do that. So determinant from SP to NR to really this plus. Actually, I have shown that if some matrix preserves a bilinear form over R or C, then it takes a really value inside 1 or minus 1. So determinant is continuous, and since this SP to NR is connected, you get that we get determinant of SP to NR is 1. This is the thing, and similar thing actually. Did I? This is for SPP comma Q. Okay, SPP per Q also I have not shown that. I have not told her. Let us write that. Okay, so this finishes about this SP2 in R. So now, okay, so SPP comma Q is really what? This is T belongs to M. So let us write digression. This SPP comma Q, what is the definition? This is equal to T belongs to M to P plus 2QC, so that Tj is equal to Jt bar and okay, what was that condition? T star, okay, Kp comma Q dot T is equal to Kp comma Q. Okay. Now, so let T belongs to SP P comma Q. This implies Tj is equal to Jt bar, and from this condition I have shown that determinant of T, this belongs to R. This is a real number. So now, as T star Kp comma Q, T is equal to Kp comma Q, and you take determinant in both sides. So determinant of T star and determinant of Kpq into determinant of T is equal to determinant of Kp comma Q, and you cancel out this thing. So you will get that mod of determinant of T square is equal to 1, and determinant of T, since determinant of T belongs to R, T belongs to R, this implies determinant of T is plus minus 1, 1 and minus 1. Okay, determinant is 1 or minus 1. Now you apply the same error, since determinant from SPP comma Q to 1 minus 1 is continuous, and SPP comma Q is connected. We get determinant of SPP comma Q is 1. So this is actually I left this in detail. So now I really completed everything. Now next thing you were SP2MC. So SP2MC. So let U V U prime V prime belongs to Cn. So W of U V U prime V prime. This is like U dot V prime minus V dot U prime, and W is a non-degenerate anti-symmetric polynomial. Symmetric.
It is complex in the product, right?
Sir?
It is complex in the product.
No. Just dot product. This dot you mean, sir? This is not complex in the product. This is a dot in the product. So Z1, Z2, Zn dot. Just multiply this thing. Everywhere this dot means this just multiply component weight. There is no, this is not in. So this is the thing. So W is a non-degenerate anti-symmetric bilinear form. Bilinear form over C. And so associated matrix is similar thing. It's with respect to standard basis is J1 is equal to 0, I minus I0. This is equal to minus J. So SP2NC, you really take this thing that A belongs to M2NC, so that A transpose J1A is equal to J1. And this is really A belongs to what? M2NC, so that A transpose J is equal to J, and this is A belongs to GL2NC, so that J is equal to J. Now it is clear that SLSP2NC is a pseudo-algebraic. Actually, by the way, some books actually also write this SP2NR by this thing SP2NR. They write as SPNR, and that is a really a confusing thing. Uh, and similarly SP2NC they write as SPNC, and in some books write SP2NR, some books SPNR. So there is some confusion, but you should be really you should guess on your own that what is the notation the book is using. Okay, so this is the thing. From this definition, see that it is easy to see that SP2NR is contained inside SP2NC, and this is SP2NR is really unbounded, and because it contains a GLNR, and you can also show that SP2NC contains a copy of GLNC. You can also show that, but since you know that SP2NR is unbounded, so this implies this SP2NC is non-compact. Okay, so I will also leave the thing. It is also easy to see that SP2NC is closed under conjugate transpose. So I will give this thing as exercise. I have really done this various times, so you will get the same size and
Conjugate exercise.
conjugate, sorry, Laurent conjugate transpose. Sorry. So with this, actually, I will stop, and in the next lecture, we will prove that this group is connected, and also we will hopefully we will calculate the fundamental groups of all the groups which I have seen, and also if possible we will start something I do not know, maybe it is not possible to start on tomorrow symmetric space, and after finishing this thing I will take one lecture or two lecture probably developing some preliminaries about Riemannian geometry which will be used. So is there any question, or I will like to stop here.